Good evening. Today we are going to start the new chapter, third chapter called current electricity. We've been dealing with electrostatic. The first two chapters together are called electrostatics because the word static would mean stationary. So if you would have noticed, the first two chapters we dealt with charges which are at rest. Take a dipole. Dipole is two equal and opposite charges which are at rest. Take capacitor that we learned. The charges are rest on the plates of the capacitor. So the first two chapters deal with charges at rest, and therefore together that chapters are called electrostatics because the word static stands for stationary. We are now going into the new chapter called current electricity, where we deal with the physics behind charges in motion. The introduction to this chapter has already been done to you in class 10, so it's not a new topic to you. You know Ohm's law, all these topics come under current electricity. So you already know that in a good conductor, suppose I'm going to draw a cylindrical conductor like this, a cylindrical conductor, we know that there are positive ions which are vibrating in their own fixed positions. There are also free electrons. The free electrons, any good conductor has free electrons which are free to move. That means they are free to conduct electricity. Now, these electrons, on the application of an electric field, suppose you connect it to the terminals of a battery of voltage V, this end is positive and this end being negative, we are applying an electric field directed from the positive to the negative. So every electron is under the action of an electrostatic force, and the force experienced you already know from the first chapter is given by the formula Q times E. Here I will replace Q with a minus E because charge on an electron magnitude is 1.6 into 10 raised to minus 19, that is E, and the electron is negatively charged. I have given the negative sign here to show you that the force experienced by the electron will always be opposite to the direction of the electric field. So if your electric field is in this direction, all of these electrons are going to experience an electrostatic force opposite to the electric field and therefore move towards the positive terminal of the battery. So this now we have charges flowing through the conductor, and in 10th standard you already know the definition of current as the rate of flow of charge. That is, if dq charge flows through a point in the conductor in time dt, then the current is said to be dq by dt, defined as the rate of flow of charge. You know the SI unit of current also is 1 ampere. 1 ampere from here is equal to charge is 1 coulomb by in 1 second. So 1 ampere can be defined as that current. A current is said to be 1 ampere if a charge of 1 coulomb flows through the conductor in 1 second. So this is the SI unit of current. So this portion I know that you already know from 10th standard, current being the rate of flow of charge, and also the SI unit of current is 1 ampere. Current, I hope all of you know, is a scalar quantity. Now I'm going to introduce a new topic to you called the drift velocity. Now here in this conductor, suppose we take the case before the application of the electric field. You have not connected it to the terminals of the battery. There is no electric field applied to the conductor, and you know there are free electrons. All of these free electrons, while moving through the conductor, will undergo collision with the positive ions, and after every collision they will change their direction. The velocity changes in direction, and they will have velocities in all random directions. If you have a velocity, one electron having a velocity in this direction, after one collision it may change its velocity to exactly opposite the original. So you have all these electrons in random motion, and therefore if you take the average initial velocity of all these electrons, the average velocity is going to be a 0 because they are all directed randomly, no particular direction. So the average initial velocity is going to be 0. Now the moment you apply a battery, you connect the two ends of the conductor to a battery of V volt, you are now applying an electric field in this direction, and all these electrons are going to experience this electrostatic force, and because of this electrostatic force they are all now going to start moving towards the positive terminal of the battery. This, and now if you take the average velocity is what you call as drift velocity, denoted by the letter Vd. Now all of these electrons experiencing the force in the same direction are going to move towards the positive terminal of the battery, and the average velocity with which they move in the electric field, that average velocity is what of these electrons is what you call as the drift velocity. To find an expression for this drift velocity, we go to the equations of motion that we know, V equal to U plus AT. Now in this, if I take the first electron, V, after the application of the electric field, its final velocity is V1, initial velocity U1 in a time T1. Now here, acceleration A, as you know, is F by m from the equation F equal to ma. This F is the electrostatic force experienced by the electron given by the equation QE. But you remember I replaced Q with minus E because charge on an electron is negative and it is magnitude is 1.6 into 10 raised to minus 90. So we have this as minus EE by m. Now all electrons will have the same acceleration because charge on an electron is the same, all electrons. All of these electrons are experiencing the same electric field and the mass of all electrons will be the same. So all electrons will have the same acceleration, so I don't have to use A1, A2 for different electrons. Now if I take another electron, V2 is going to be U2 plus AT2 and so on up to the nth electron being Vn equal to Un plus Atn. Now average of all these final velocities on the application of the electric field is what we defined as Vd, the drift velocity, is equal to, remember I told you the average of the initial velocities of all the electrons is 0. So this is average now to be 0, equal to A into tau being the average of this time, that is, this is called the relaxation time. It's not a new term to you. In 11th standard we learned this chapter called kinetic theory, in which I had introduced this tau called the relaxation time, that is the time interval between two successive collisions of this electron. So between one collision and the next collision, the time gap or the time interval between two successive collisions is what you call as, that average time is what you call as tau, the relaxation time. So if I substitute this A as minus EE by m, we have the formula for drift velocity as minus EE tau by m, showing you that since electric charge and mass of an electron is a constant, the drift velocity depends on the electric field that you apply and the relaxation time tau, which is dependent actually on temperature, because if you increase the temperature of the conductor, then the collisions are faster and the time gap between two successive collisions will be lesser. So greater the temperature, lesser will be the relaxation time. On the other hand, if your conductor is cooled, then the collisions will be far apart and the time interval between two successive collisions will be larger. So lower the temperature, greater the relaxation time. Now you can also have another formula for this, because I already taught you in the second chapter equation which tells you the electric field is minus dV by dx, where the negative sign tells you that the electric field is in the direction of decrease in potential. That is, this was the positive end, this is the negative end. As you go from this end to this end, the potential decreases and electric field is in that direction. So if you're just talking about the magnitude of the electric field, dV by dx would mean between the two ends of the conductor, the electric field is, the potential difference is V, and the distance between the two ends will be the length of the conductor L. So from this formula, I may write E equal to V by L for any conductor. So if I'm going to substitute that here, then this equation will become minus EV tau by ml, where E I have replaced with V by L. So now you have two equations for drift velocity, EE tau by m and EV tau by ml. You don't have to bother about the negative sign. It is just there to show you that the electron is negatively charged. And you need to remember the magnitudes as either EE tau by m or EV cho by ml, where E and M, you must remember, are always a constant standing for the charge on an electron and the mass of the electron. Now, knowing two equations, that is, now I introduce current to you as Q by T and a new quantity, drift velocity Vd equal to EE cho by M or EV cho by ml. Our next aim is to find an expression for current in terms of this drift velocity. You already know current as Q by T. We are now going to find a new expression for current in terms of this drift velocity. That's also very simple. Here you have a conductor, and in a conductor the number density means the number of free electrons in unit volume. It's different, it's a constant for different materials. Like copper has a large number density, it's a very good conductor, so there are a large number of free electrons in unit volume, and therefore the number density is also very high for copper. So N is the number density, meaning the number of free electrons available for conduction per unit volume in any conductor. So if it's a very good conductor, the number density is also very high. Now this shows you that the number of electrons total in the conductor should be equal to N into volume. Volume of a cylindrical conductor, as you know, should be base area into height, where this is the length of the conductor. So this number of electrons will be N into, instead of volume I may write base area into height, which is the length of the conductor. If you know the number of electrons, that is N into A into L, then I can find the total charge in the conductor, because total charge in the conductor Q must be equal to NaL into E, because NaL is the number of electrons and E is the charge on each electron. So total charge will be total number of electrons multiplied by the charge on each electrons. That's how I got the expression NaLe. Now time taken for the electron to move from this end to this end, that is a total distance L. You know time is distance by speed or velocity. The distance that it travels is the length L of the conductor. So that's L divided by the velocity with which it travels under the application of the electric field, that is when you've connected it to a battery, will be the drift velocity V. So now I know I equal to Q by T. This I already know. I'm going to substitute for the total charge in the conductor Q as NaLe from here, and divided by the time is L by Vd. So this Vd I'm going to write on top. So this L and L, if I cancel, I get the equation for current as NeAVD, and this is what we wanted, the expression for current in terms of drift velocity. So this is current I in the conductor. N is a number density of the conductor, which is a constant for a given material, number of electrons in unit volume. E is the electronic charge, again a constant, 1.6 into 10 raised to minus 19. A is the area of cross section of this conductor, and drift velocity is Vd. Drift velocity, as I just told you, is the velocity with which, the average velocity with which these electrons move towards the positive terminal of the battery or move inside an electric field. So we have now got a relation for current in terms of drift velocity. After this, I am going to introduce another new physical quantity to you called the current density. Current density denoted by the letter J. J, small j, is equal to I by A. That is, suppose we have this as your conductor. This is your conductor and your current is flowing through the conductor like this. Now, this is the area of cross section of the conductor. How much current passes through the conductor in unit area is what you call as the current density. So current passing through unit area of the conductor is what you call as current density. From the first chapter, we have been dealing with area as a vector quantity. The direction of that area vector being perpendicular to the area itself. So if your area is like this, the area direction of that area vector will be perpendicular to the area. Now here we have, therefore, area being a vector, J is also a vector quantity, current being a scalar quantity. Its SI unit current is ampere per area will be meter square. So this is something new to you. You have not learned this in 10th standard. Current density J is I by A. SI unit is ampere per meter square, defined as the current passing through unit area of a conductor. And this is a vector quantity. Now, from here, we go on to the next topic in our textbook is Ohm's law. That I'm sure all of you know from 10th standard. Ohm's law simply telling you that if you have a resistor connected to a battery like this of V volt and current I, this is resistance R. This V is directly proportional to I, or V is equal to I into R, where R is called the constant of proportionality, and R, as you know, depends on rho L by A, where rho is the resistivity of the conductor, depending on the material of the conductor. You will now further, in the next few topics, you will see rho not only depends on the material of the conductor, of the resistor, it also depends on the temperature. Then we have L as the length of the resistor and A as the area of cross section. And so the resistance is a constant depending on the material that you have used, constant depending on the temperature, it's a constant depending on the length of the resistor and the area of cross section of the resistor. This R is a constant of proportionality here in Ohm's law. Now from here we may write, so V equal to I into R. This V for any conductor or for this resistor, V equal to E into L from this one, that is V by L is equal to E. So from, I hope you remember this, just now I told you E equal to dV by dx. Between the ends of a conductor, we have V as the difference in potential, L as the distance. So E equal to V by L, and from this equation we may write V equal to E into L. So this I may write as E into L is equal to I into rho L by A. If I cancel this, and this I by A is what you call as the current density J. So we have E equal to J into rho, where electric field is a vector, current density is also a vector, but resistivity rho is a scalar quantity. So we have E equal to J rho, rho being the resistivity of a conductor, J being the current density, and E is the electric field. So we have this which you already know from the 10th standard, nothing new to you. Only this formula, that is relation between electric field and current density, is new to you. This resistivity, I hope you remember, is also reciprocal. You know something called as conductivity sigma being reciprocal of resistivity. And so this formula can also appear as J by sigma, because 1 by sigma is rho. So you have E as J rho, or inverse of rho is what you call as sigma. So it can also be written as J by sigma. Sigma is the conductivity. Resistivity SI unit, I hope, is you know already as ohm meter, and therefore conductivity is ohm minus 1 meter raised to minus 1. So these are all things that are just revision of what you already know in the 10th standard about resistance, about resistivity. So as you see, resistance is directly proportional to the length of the resistor, inversely proportional to area of cross section of the resistor. But resistivity is a constant, because resistivity would mean, how do you define resistivity from here? Resistivity rho is equal to RA by L, and if this is taken to be 1 meter square and this is 1 meter, then you see rho is equal to R. So in 10th standard you have already defined resistivity as a resistance of a wire whose area of cross section is 1 meter square and length is 1 meter. So resistivity cannot change unless you change the material, or we are going to see that now we are further going to see that it depends on temperature also. But otherwise, If you've not changed the material and if you've not changed the temperature, you always talk about resistivity as a resistance of a material whose length is 1 meter and area of cross section is 1 meter square. So we have resistivity as a constant for a given material at a given temperature. You may also be asked to derive Ohm's law from this equation, which is again simple. We have the equation E equal to J rho. We also know E equal to V into V by L. E equal to J rho, which we derived just now. This from E equal to dV by dx. Across the conductor, the potential difference is V and the length of the conductor is L. So since both the left hand sides are the same, I may write J rho equal to V by L, or J being current density I by A into rho is equal to V by L, or I is equal to V into, I keep V here, so V is equal to I into rho L by A. This rho L by A you know is resistance. So this I may write as V equal to I into R being a constant, I may write V proportional to I. So you may also be asked to derive Ohm's law or arrive at Ohm's law from this equation. Or previously what we did is, we started with Ohm's law and arrived at this equation. You may also be asked to arrive at Ohm's law from this equation. This is how you will do. Okay. Now this resistance that we've been talking about is, I hope, very clear to you that resistance R equal to V by I. So if you draw the VI graph with I here and V here, we must have a straight line because R is a constant. So if the voltage increases, the current also will increase, keeping R a constant. So which means the slope of the graph V by I should give you the resistance R of that material. So resistance R is the slope of this VI graph. But we also know R is not dependent on VI, meaning if V increases, I also should increase, which will give you R. R is a constant which depends on rho L by A. So when you make the resistor itself, its resistivity of the material that you have used, then length of the conductor and area of cross section of the resistor will already decide the resistance of the resistor. Now I've drawn one resistor for you to see. Resistors, what we use now are carbon resistors. Carbon resistors, which are actually, with a binding agent, they fuse this carbon and bring out this resistor. You must have seen this in all electrical circuits. I actually broke this leg of the resistor. I'm sure all of you would have seen these resistors in your electrical circuits. And you will see that all these resistors have rings on them. In your textbook, and you need to know how to read the value of a resistor based on the color coding of the rings that they have shown here. So in this particular topic, we have called the color coding. It is there in your printed notes that I've sent you on page. This is on page 30 of your notes. You have the color coding. Color coding would mean you start with black, brown, red, orange, then yellow, green, blue, violet, grey and white. Start with a 0, 1, 2, 3, 4, 5, 6, 7, 8 and 9. Then you have a gold, silver, and no color. This is 5%, this is 10%, and this is 20%. Let me explain this to you. Now, and you're going to use this color coding to help you read the value of the resistor that I'm showing you. I don't know if you're able to see the color of the ring on that resistor, but I can tell you that the first ring is brown. So brown, if you see, stands for digit 1. So the first line here, the ring here, stands for 1 because it's a brown color ring. The ring next to that, the second ring, is black in color, and black, as you know, is 0. So the second digit is 0. Then the third ring here is red in color, and the third ring stands for the power of 10. So this will be into the power of 10. Red ring would mean power of 10 is 2, red color. And then we have a silver ring here. The last ring, the fourth ring, is a silver ring. And a silver ring would mean that there is a 10% tolerance. That means the resistance can be plus or minus 10% tolerance. And so many ohms. So this is how you would read the value of a resistor in any given circuit, because every resistor that you have in a circuit will have these colored rings. The first color will stand for the first digit. For example, suppose the first color ring was yellow. Yellow ring would mean the first digit is 4. Suppose the second color ring was, let's say, violet. Then the second digit would be 7. The third ring would always be for the power of 10. So multiplied by, let's say the third ring was orange. So then we have 10 raised to 3. And in case we don't have a fourth ring, that means no color, then the tolerance is 20. And this will be your value of the resistor in ohms. This would be that there can be a change of 20% in the total value. So this is how you will learn how to read the value of a given resistor from the colored rings that they carry. Any circuit. This I actually got from one of my chargers. Most all your electronic circuits will carry devices like this, which is called as the resistor. Now to by heart this, what I use is B.B. Roy. B.B. Roy of Great Britain has a very good wife. Okay. B.B. Roy of Great Britain has a very good wife. So you can use B for black, brown, then this is red, this is orange, yellow, green, blue, violet, grey and white. You start with 0, you end with 9, and then you can read the value of your resistor. I just told you that resistance depends on resistivity, and the resistivity actually depends on temperature. So we are now going to see how your resistivity depends on temperature. That's our next topic. Resistivity in 10th standard, you've been learning, is a constant that depends on the material. That's what we taught you in 10th standard. But now you need to know it is dependent on the type of material, but it also depends on the temperature of that material. So here we take Ohm's law as V equal to IR, and instead of I am going to use the formula NEAVD, because we just derived this relation for current in terms of drift velocity, and R I am going to substitute, which you already know as rho L by A. This is going to be equal to NEA. For VD, I taught you a formula EV2 by ML. This we just derived now. E into rho L by A. And this is what we have as V. Now this L and this L I can cancel. This A and this A I may cancel. This V on the left hand side and this V on the left hand side I have cancelled, so that this leaves me with 1 here. And so if I leave rho on this side and bring all the other terms to the left hand side, I have rho here. This goes on top as M by This comes down as Ne square 2. So we have this new formula for resistivity which depends on M by Ne square 2, where M is a constant always. It stands for the mass of an electron. Then E again a constant, 1.6 into 10 raised to minus 90. N is the number density, which I told you is the number of electrons in unit volume for any material. So for a material, this N should be a constant because it depends on the material. Naturally, the number of free electrons available in unit volume is a constant for a given material. Then tau, I told you, depends on temperature. Tau stands for the relaxation time, that is time gap between two successive collisions. So if the temperature is very high, the collisions are faster, the relaxation time becomes smaller. If the temperature is lower, then the time gap between collisions will be larger, and therefore lower the temperature, larger the relaxation time. That's why I told you rho actually depends on the type of material, which determines N. It also depends on the relaxation time, which depends on the temperature. Okay. So now that you know this, we can go into three very important graphs. The graphs are for any conductor, good conductor, let's say like copper. Our example will be copper. For any good conductor, we have the resistivity versus temperature graph like this. Let me explain the graph to you. We know rho equal to M by Ne square 2. Now, as the temperature goes on increasing, we know that the collisions are faster, and if the collisions are faster, then the relaxation time will decrease because collisions are faster. So the time gap between two successive collisions will decrease, and the moment tau decreases, resistivity will increase. So this is M, the mass of the electron, which is a constant. N, number density for a conductor is a constant. E, the electronic charge, is a constant. So your resistivity is inversely proportional to relaxation time. That means it is directly proportional to temperature. Now the same explanation goes for an alloy. An alloy like, let's say, nickel is an alloy. The same explanation. We have an increasing graph. But in your textbook, the graph has been given like this because they have taken a range here as 200 degrees Celsius and so on. So above this temperature, your graph will become, it is like the previous one, resistivity goes on increasing with temperature, but above 200 degrees Celsius, the kind of graph that you get will be this. Then the next graph that you need to remember in this topic will be that of a semiconductor, which behaves just like the graph is just like that of an electrolyte. Now, semiconductor, you do not know about it. It is something in between a conductor and an insulator. But you don't have to worry about not knowing about it simply because we have a huge chapter. Chapter 14 is all about semiconductors. And when you learn that chapter, this will become very simple to you. Electrolyte you already know. Like for example, if you have an electrolyte CuSO4 or NaCl, you know that these ions will split into Na plus and Cl minus. And in that case, what happens is, we are not actually talking about number density because number density is what? The number of free electrons available for conduction in a conductor. But in an electrolyte, it is not the free electrons that are conducting the electricity. It is these ions, the positive ions and the negative ions, which move towards the electrodes. So there, this number density is not important there. Instead, this relaxation time is not important simply because relaxation time is the time interval between successive collisions between electrons and the ions in a conductor. But here, number density becomes important because I hope you know in chemistry from 11th standard, if you warm the electrolyte or if you heat the electrolyte, the dissociation is more. Na plus and Cl minus, dissociation of these ions is more. So at higher temperatures, you have larger number of ions because the dissociation is higher. So you have larger number of ions, which means the number density is larger, and because of which the resistivity is lesser. So if you draw the graph for a semiconductor, which is the graph is same as that of an electrolyte. I am not explaining that of a semiconductor simply because we do not know anything about a semiconductor right now. You will only be learning it in chapter 14. But you know about an electrolyte, that as you heat the electrolyte, the dissociation is larger and therefore the number of ions ready for conduction is higher. Higher the number density, lesser will be the resistivity. So we have a graph which is a decreasing graph like this, both for semiconductor and for electrolyte. So these are the three graphs that are very important based on this equation that we derived for resistivity, that is m by ne squared 2. You need to know the derivation also. Another thing that we have just before, I think I should have discussed it along with Ohm's law. It's something that you need to know. That is, there are some limitations for Ohm's law. That is, there are some materials that do not obey Ohm's law. Limitations, drawbacks of Ohm's law. That is what we are going to discuss now. There are some materials, like I told you about the semiconductor. Semiconductors do not obey Ohm's law. Some semiconductors I will name. One semiconductor is the diode. Again I repeat, these may be new terms to you, but you don't have to worry because these terms will become really familiar to you when you do the 14th chapter. So all semiconductor, one of them is the diode. Its VI graph is like this. You have the V here and the I here. Your VI graph for any semiconductor looks like this. So you see, Ohm's law says that VI graphs should be straight lines whose slope is given by the resistance. But you will see that the VI graph for any semiconductor, for a diode, is a non-linear graph, which means this material does not obey Ohm's law. So that's a drawback, that's a limitation of Ohm's law, because Ohm's law is not obeyed by all materials. We have another semiconductor called gallium arsenide, GaAs, for which the graph looks like this. VI graph is a graph like this, which means that again this is a non-linear graph, and for the same current I happens at two different voltages, which is not true in any case of Ohm's law, because in Ohm's law we have a straight line, we have the I here and V here. Please note the difference here. So we have only one current corresponding to one voltage. You can't have two different values of voltage corresponding to a single current value. So this is another material, gallium arsenide, again a semiconductor which does not obey Ohm's law. The third limitation of Ohm's law is, if you have the VI graph, you expect all materials to have a straight line, slope given by the resistance. But you will see, as you increase the current, the resistor starts getting heated up, and as the temperature changes, you know, resistivity changes. I just showed you that for all conductors, there is a change in resistivity. We saw the graph here, resistivity versus temperature graph like this. So we have, based on the formula, m by ne squared 2. So as resistivity goes on changing with temperature, when you pass larger currents, the resistor gets heated up, and if the resistor gets heated up, its resistivity will change. If the resistivity changes, then naturally the resistance is also not a constant. So then you can't have a straight line, and you will see that your line is no more a straight line. At higher current values, because of larger temperatures, there is a change in resistivity, and therefore there is a change in resistance. So this again is a limitation of Ohm's law, because then at high temperatures V not proportional to I. So these are the three limitations that are given in your textbook. That one is this one, and the other is that Ohm's law is not obeyed by materials called semiconductors. Then there's one more small topic that I need to discuss with you, which is topic 4 in your printed notes, called mobility, denoted by the letter mu. Very simple. Mu is simply drift velocity per unit electric field. That is, if you have a conductor and you apply an electric field which is equal to 1 Newton per Coulomb for unit electric field, the drift velocity of these electrons is what you call as mobility. It is a, you just take the positive values, mobility is Vd by E. Now, Vd as you know is E tau by m. So we have E tau by m by E. So then we know this is E tau by m. Your mobility, which is drift velocity per unit electric field, depends only on E tau by m. E and m being constants. E is the electronic charge, m is the mass of the electron. Tau, as you know, is a relaxation time which depends only on the temperature. So we will now come to the end. We have now come to the end of the first session, and many of the topics are familiar to you. What we discussed today is we discussed current, definition of current as Q by T, which you already knew from 10th standard. We also discussed Ohm's law. From Ohm's law, we came to the equation that relates electric field to current density, E equal to J rho. And I told you J is the current density, current per unit area, which is again a new topic to you. Then we went on to discuss what drift velocity is. That is, initially before you connect your conductor to a battery, all of them are in random motion. So if you take the average velocity of these electrons, it averages out to be 0. But the moment you connect it to the terminals of a battery, there's an electric field, and the electrons travel in the electric field in a particular direction towards the positive terminal, and the average velocity with which they travel towards the positive terminal of the battery is what you call as drift velocity. And then what we did is we found a relation for current in terms of drift velocity, I equal to NEAVD. Then we discussed Ohm's law. We also discussed the limitations of Ohm's law. From Ohm's law, we went on to resistance because Ohm's law, V equal to IR. R is a constant of proportionality which depends on rho L by A. I also introduced to you this new way of finding out the value of a resistor in a circuit by simply looking at the colors of the ring on the resistor. Then we went on to derive an expression for resistivity in terms of relaxation time, rho equal to m by Ne squared tau. And from that formula, we again have 3 graphs. One graph which shows you the dependence of resistivity with temperature for a good conductor like copper, also for an alloy like nichrome, and also the graph for resistivity versus temperature for semiconductor and electrolyte. You also need to know what is mobility. Mobility being mu, that is drift velocity per unit electric field. Now, also let me tell you one last thing. That is, we know that the resistance now actually depends on temperature. So you know that the resistivity and therefore the resistance of a material will go on, or if it's a good conductor, will go on increasing with temperature, because you saw the graph. It's resistivity versus temperature graph for a good conductor is a increasing graph. So to find out the new resistance at a higher temperature, we have a formula RT equal to R0 into 1 plus alpha into T minus T0. Let me explain this to you. This initial, suppose we have, let's say we have a conductor whose initial resistance R0 is, let's say 5 ohm, and this happens at room temperature, which is 27 degrees Celsius. Now what you do is you heat it. So this is your initial temperature, that is, this is your initial temperature 27 degrees Celsius. This is your 5 ohm initially at room temperature. This was your resistance of the conductor. Now the moment you increase the temperature, you know the resistance also will increase. So the increased or the new resistance is what you call as RT, and the new temperature to which you have increased is what you call as T. So in this equation, I hope you know R0 is the original resistance at temperature T0. You have increased the temperature from T to T0, from T0 to T. Your resistance will now increase from R0 to RT. Alpha is called the temperature coefficient of resistivity. You can see that it can be defined like this. See, from this equation, if I open the bracket, RT is equal to R0 plus R0 alpha into T minus T0, or RT minus R0, I brought this here, by R0 into T minus T0 is what you call as this alpha, which is temperature coefficient of resistivity. Now, this one's SI unit is ohm, this is also ohm, so that is there, this is Kelvin. So you will see the SI unit of Kelvin should be K raised to minus 1, because this and this ohm will get cancelled and you have K raised to minus 1. Dimensional formula will be M0 L0 T raised to minus 1, because this is temperature on top. So this is called temperature coefficient of resistivity, which is defined as the change in resistivity. RT minus R0 is change in resistance by original resistance and also for unit rise in temperature, because you're dividing it with R0 and T minus T0. You may define this alpha, temperature coefficient of resistivity, as the change in resistance for unit resistance and unit rise in temperature. So this is the end of the first session of current electricity, and we have probably 3 or 4 sessions more on this chapter, and I hope you enjoy this chapter because it's a really interesting chapter. Thank you.